We have finished with simple decision trees for the moment. We're now going to talk a little bit about bagging and then move on to random forests. Bagging stands for bootstrap, aggregating. Rather than talk about what it is, I want to just simply show you what it is. So here we are back in R, and we are going to fit a tree. We've got a particular complexity parameter which is chosen to be fairly sensible, along with that minimum split parameter we talked about previously. We will only split a leaf into two leaves if there are at least 32 observations in that leaf in our training data. Create the tree, which was quick. Find the train and validation error, 17,000 and 20,793. Let's fit the same tree again. Do you think we're going to get the same result? Let's try. Well, of course we got the same result. There is no randomness in decision trees. The data was the same between the two trees, the features were the same, and which features to use and how to split them in order to minimize the loss function is therefore going to be exactly the same. Same tree, same result. What we are going to do, though, now is to use different data for the two trees. Bootstrapping a dataset means randomly sampling with replacement from that dataset. If you have 1,000 examples, then bootstrapping means you randomly select 1,000 examples with replacement from that dataset. If you think about what that means, you can do it, you can randomly select 1,000 times. Obviously, some examples will come up twice, and some examples will come up not at all. On average, we expect 2/3 of the examples to be picked. We are going to sample with replacement, and sample over here is the same as the number in design. So we're going to, if we have 2,000 lines in our dataset, we will sample 2,000 lines with replacement from our dataset. Some lines in our dataset, some houses will be sampled twice, some houses will be sampled not at all. Let's just see how long this thing is. 2,062 of them. Let's see how many unique houses have been sampled. 1295. Interestingly enough, what proportion of the houses are present in the data? About 2/3. That is a standard result in bootstrapping, that if you bootstrap with replacement the same number of times as you have data points, you should expect that 2/3 of your houses will be in your final dataset. Every time we do this, we're going to get a different bootstrap sample. What happens if we now grow decision trees over these different bootstrap samples? So the first sample, we can see before we did have train error of 17,000 and validation of 20,000. The train has gone down and the validation has gone up. That is definitely worse. Test error is worse. Overfitting is worse. But let's do the same again. Let's create another tree on a random data set. Again, a random bootstrap sample. Once again, it's different, but it's still worse in every day. It's still worse in every way. So we haven't gotten very far. What have we done? We've grown two different trees using bootstrap samples. Each tree individually is worse than our original tree. How about the correlation in predictions? Are they predicting exactly the same thing? Well, obviously not. The trees are different. But you can see there is a high correlation, but not a correlation of 1. So we've done bootstrapping. Bootstrapping alone was not much use, but now let's aggregate. Let's do the ag part of bagging. I'm simply going to predict the average of the two trees. Now, our original test error was 2793. This isn't just a reasonable improvement, this is a massive improvement. The bootstrapped aggregated loss is much better than the original. Why? Why is it so much better? I've heard the following explanation. I don't know if it's the correct one, but it kind of feels good to me. When you have two trees and they're grown over random samples of your data, in those two random samples, each of them, you have two things. You have the signal and you have noise. Now, the signal in both trees is going to be the same because, if you like, that's the underlying truth, and the underlying truth will always be present in whatever data sample you are using. So the signal in the two trees will complement itself, and when you take the average over two trees, you will accurately pick up the signal. But how about the noise? What will happen in the noise between the two trees? Well, since we have randomness, the noise in one tree is quite likely to be different and possibly in an opposite direction to the noise in the other tree. If you are lucky and the predictions in your trees are not 100% correlated, the noise will to some extent cancel itself out, especially if you bootstrap lots of times. So the signal gets stronger and the noise gets weaker. What does that mean we're going to do? It really means we are going to get rid of some of the variance in your tree. So bagging is a great way to get rid of variance. Bagging was the first improvement to decision trees, but the thought process immediately carries on from there. Besides bootstrapping the data and then aggregating the results, can we inject randomness into our trees in other ways so that the signal is always there, but the noise becomes even less correlated between trees, and so stands a better chance of cancelling itself out? Well, yes, there are different ways of injecting randomness into trees before we aggregate them, and when we're doing that, we are creating random forests.